So let's get started. Today we are going to elaborate more on the how to solve 2D problem using the equations of equilibrium. Last time we managed to solve 2D problems using the equations of equilibrium, but all the forces was concentrated forces. So the forces was like that, concentrated forces. But sometimes a body or a beam is going to be subjected to a loading which is distributed over a surface. Not like the load is going to be directed to a specific point. For example, the pressure of a wind on the face of a sign. So if you have advertisement, you see advertisement a lot, sign for advertisement, and the forces that is going to be subjected to the sign of advertisement are going to have the wind. And sometimes if the wind is so high, then the sign is going to turn over. And also the pressure of the water within the tank. It's just like a load which is distributed over a surface. And also the weight of a sand on a floor or a storage container. All are distributed loading. Here, for example, we have a beam. We have a number of bricks. It has been set up so that it looks like a triangular distributed loading. So we need to know how to deal with such cases. So in order to deal with that type of the force, first we need to know the intensity of that force. In order to measure the distributed loading is going to be Newton per meter or pound per foot if you are going to use the US customary. And like you can see here, it's just like a force which is distributed over a line. That is why here the intensity is force per distance. And in order to deal with distributed loading, I need to it's need to be represented by a single resultant force. So instead of having distributed loading like this one here, we are going to express it as only one single resultant force. So how I'm going to know the resultant force? That resultant force is going to be equivalent to the area under the loading. So here is the area under the loading. If you calculate the area under the loading, then you are going to get equivalent resultant force. Then once I know the amount of the resultant force, I need to know the location of that force. The location is going if you are going to draw the line of action for that single resultant force is going to pass through the centroid or the geometric center of that area. So the line of action of the equivalent resultant force is going to pass through the centroid or the geometric center of that area. So we have a different type of distributed loading. It could be triangular distributed loading like this one here, or it could be rectangular distributed loading like this one, or it could be trapezoidal distributed loading like that one. So I'm going to show you how we are going to deal with them. I'm going to give you examples for that. Most of the cases that we are going to encounter is going to be either this case or that case or a case like that one. If you understood how to deal with these three cases, you are going to be able to deal with all of the cases. Of course, if the shape here was not regular shape, in that case, I need to use the integration in order to find the area under the curve. But most of the cases here is going to be like these three basic shapes. So let's see example. We are going to I'm going to give you I'm going to give you rectangular distributed loading, and I want you to evaluate the equivalent resultant force, and also I need to know the location. So like you can see here, we have rectangular distributed loading like this one. The intensity of the distributed loading is 100 Newton per meter. This represents the height, and here we have the base, which is 12 meters. It's required to calculate FR. We need to get the equivalent resultant force for this system here. Like we said that in order to calculate the FR, we are going to evaluate the area for that diagram. So here is the height, and here is the base. We are going to say that the area equal the height times the base. We are going to end up with 100 times 12, which is 1,200 Newton. Now we expressed that system with a single equivalent or single resultant force. Then we need to know the location of that force. So the direction, of course, is going to be down, like those here, but we need to know the location. So the location is going to be somewhere here, and since we are dealing with rectangular here, the distance is going to be exactly at the middle, because the centroid is here. If you are going to evaluate the geometric center of that area, is going to be here. So if it's required for you to know the distance from here to here, it's going to be 12 over 2, which is 6 meters. Another example, here we have rectangular distributed loading, like you can see here. The intensity from here to here equal 100 Newton per meter, the height here, and the base equal 12 meters. We need to know the resultant force resultant for that system. So we are going to evaluate the area here. The area is going to be half times the base, which is 12, times the height, which is 100. So we are going to have 6 times 100, which is 600 Newton. Also, we need to know the location. So the location is going to be somewhere here. Since this is triangular, the location of the resultant force, it's going to be close to the left, because the area here is small while the area here is bigger. And we say that the location is going to be based on geometrical center of that area. So of course it's going to be here, and we know that the centroid for triangular is going to be about 1 over 3 here, and from here it's going to be about 2 over 3. So the distance here, the distance here is going to be 1 over 2 times 12, which is 4. So here we have a 4, and here we are going to have 8, because if you multiply 2 over 3 by 12, you are going to get 8. So now we are going to get equivalent for the distributed loading like that, and also we will be able to know the location. Why the location is important? Because without the location, I'm not going to be able to calculate the moment. So now I can treat the problem like if it's the concentrated force. So let's look at that example. Example number 3. We got example 1 and 2, which contained only concentrated force. So this time we are going to have a problem where we have distributed loading. So here it's required to determine the support reactions. We have only one support at A, and it's fixed support. And it's mean that I'm going to have 3 reactions. We have force in X and force in Y, and we have moment. In this problem here, we are going to neglect the weight of the beam. and that is going to simplify the problem for me. So in order to solve that problem, the first step need to be done. We need to draw the free body diagram. And in order to draw the free body diagram, we need to know the X and Y axis. So the orientation of XY is going to be like that because the beam has been laid into the X direction. So we are going to establish X, Y coordinate axis in suitable orientation because the problem is like that. The suitable orientation is going to be like that. Then we are going to remove the support. We have only one support, which is at A. We are going to remove it. And then we are going to put reaction instead. Also, we are going to show all the forces. We have that force here and that force here. And here we have a couple moment. Also, I need to show the couple moment. So I have one couple moment. I have rectangular distributed loading, and I have concentrated force, which need to be decomposed into X and into Y. Like I mentioned, here we have rectangular distributed loading. So this system, I need to convert it to equivalent system by getting the area for that diagram. And then we need to know the location of the resultant force for that system. We need to label all the loadings, whether it's especially the unknowns. We need to give them letters. So here we are going to have AY, the reaction in the Y-axis. Here we have AX, the reaction in X-axis. And here we have MA, the moment at point A. So we have 3 unknowns, and the rest, we know the rest. And also we need to put the magnitude of all that forces. And also we need to put the direction. The direction is very important. And also we need to put the dimensions so that we can calculate the moment for that. So now we finish with the first step. We draw the free body diagram. And now we need to use the equations of equilibrium, those 3 equations. And in order to do that, I need to decompose all the forces into X and into Y. And also I need to convert any distributed loading system. So here I have a force like that with angle here. So I need to decompose that force into X and into Y. And also here I have distributed loading. I need to convert it to equivalent system. So if you want to get the FR for that system here, I'm going to multiply the 8, represent the height, by the base, which is 1.5. You are going to end up with 8 times 1.5, which is 120. And the location is going to be exactly at the middle of 1.5. So 1.5 over 2 is 0.75. That means the location of the equivalent force is going to be 2 plus 1.5 over 2, which is 2.75. So the distance from here to here is going to be 2.75. And also I need to decompose that force into X and into Y. In X, we are going to have 1,000 times 3 over 5. In Y, we are going to have 1,000 times 4 over 5. So now we are in position in order to use the equations of equilibrium. So we are going to start with the first one, the summation of X. Summation of the forces in X direction is going to equal 0. And we need to remember the sign convention. Here it says all the forces which is directed to the that direction is going to be positive. If it's in that direction, it's going to be negative. And let's look at X-axis. In that axis here, I have AX is going to be positive, and I have 1,000 times 3 over 5, which is negative. So this one here is positive, and this one here is negative. Now this equation is easily, since I have only one unknown, which is AX, then the AX came out to be 600 newtons. Then I'm going to use the second equation. which is the summation of the forces in y direction should equal 0. Here also the sign convention is very important. All of the forces in that direction is going to be positive. All the forces which is directed down is going to be negative. And here in y-axis we have AY is going to be positive. Directed down. And here we have that force 1000 times 4 over 5 is going to be negative as well. Here we have 3 forces. We have AY positive, we have this one negative, we have that one which is negative as well. Here again we have only one unknown. The equation is going to be very simple. We are going to evaluate the value of AY. AY came out to be 920 newtons. Finally, we are going to use the last equations, which is the summation of the forces about the point A here. We are going to, like I said before, you are going to choose that point smartly. You are going to choose that point so that you are going to end up with only one unknown. So if I'm going to take the moment here, then the AY is not going to be involved in the equation because it's not going to cause any moment. The same goes for AX. So if I'm going to take the moment about the point A, I'm going to take the moment about point A. Also, it's very important to put the sign convention. Many students forget to put the sign convention. So here the sign convention is all the moments which are counterclockwise is going to be positive. So if I'm going to take the moment here, I'm going to have MA, which is positive. Then here I have couple moment, which is negative, like you can see here. Then it's going to be minus 200. Some student multiply the couple moment by a distance. It's a couple moment. It's already moment. So please do not multiply it by any distance. Okay. Then we have the 8 times 1.5, which is 120. And we need to multiply it by the perpendicular distance. To know the perpendicular distance, draw a line of action. And then here is the point of rotation. Draw the shortest distance from here to here. And that is 2.75. And here is the point of rotation. If you push this one like that, the moment is going to be clockwise, which is negative. Then finally, we have 1000 times 4 over 5. We need to multiply also by the perpendicular distance. And also it's going to be negative because if you push from here, and here is a point of rotation, the beam is going to be rotated clockwise. So I have minus 1000 times 4 over 5 times 4, which is the perpendicular distance. All of the summation of the moments here about the point A should equal 0. Again, I have only one unknown, which is MA. I have one unknown, one equation. Then easily I can evaluate the value of MA. Okay? MA came out to be 3,730 Newton meter. So I'm going to give you a chance to ask about that example here. So do you have any questions regarding this example? Go to example 4. So now in example 4, also it's required to calculate the support reactions. This time the support reaction, it's not fixed, or it's a ruler, or it's pin. Here we put different type of supports. So at A here, we have a smooth collar. Here we have a smooth collar. Like you can see here we have a pin, which means that it's free to rotate. And also here it's smooth, which means that also it's free to move here, while you cannot move in this direction or in that direction. So I'm going to say that I'm going to have reaction which is perpendicular to that surface here because I have a smooth color at A. So I'm going to replace that support by putting reaction which is perpendicular to that surface. Here we have a rocker. We say that the behavior of the rocker is similar to the roller. So, which means that the rocker is not going to resist the moment. Also, it's not going to resist the movement into X or into Y. So I'm going to replace this one here with reaction, which is perpendicular to that surface. And finally, here we have the cable. We have a cable here, and we know that the cable can take only tension. It cannot take compression. So instead of that cable, we are going to put the same angle here of the cable, and of course, it's going to be directed out from the structure because here we have tension. Then the first step need to be done. We need to draw the free body diagram. We are going to isolate the system here. We are going to replace all the supports with reactions. So if you are going to do that, first you need to establish your XY coordinates. Here is X and here is Y in suitable orientation. Then I need to remove all the forces here, all the supports here. Then I'm going to put all the forces. Here we have concentrated force, 3 kilonewton. Here we have couple moment acting on the point B. We don't have distributed loading this time. And also we need to show all the directions and the magnitudes. We need to label all the unknowns. Here we have FA, like we said that we are going to replace the smooth color here by reaction with each perpendicular to that direction. I'm going to assume the direction. Like I said, it could be like that or it could be like that. So here in this problem, we are going to assume the direction is like that. In that here, we replace the cable and we replace the rocker by only reaction which is equal to the surface of contact. Also, finally, we need to put the dimension. The dimension is important in order to calculate the moments. So now we are going to, since we draw the free body diagram, we are in position in order to use the equations of equilibrium. So in order to use the equation of equilibrium, we need to decompose all the forces into X and into Y. So we have summation of the force in X direction equals 0. We have the summation of the force in Y direction equals 0. And the moment about any point should equal 0. So in order to use those equations, we need to decompose all the forces into X and into Y. And this time here, the tension in the cable C need to be decomposed into X and into Y. Here, the reaction acting on the collar, smooth collar here, we need to decompose it into X and into Y. Then we are going to be in position in order to calculate the other forces in Y direction should equal 0, and the moment about any point should equal 0. And in order to use those equations, we need to decompose all the forces, whether it's known or unknown, into X and into Y. So here we have FA need to be resolved into X and into Y. So FA, we are going to have FA cosine 45 and FA sine 45. And for TC, we are going to have TC cosine 30 and TC sine 30. Here we have concentrated force. Here we have a couple moment. Now we are in position in order to use those equations. So let's start with the x-axis should equal 0. The sign convention is very important. Now we are going to look at the x-axis here. We are going to have only two forces. We are going to have FA cosine 45 and we have TC cosine 30. So FA cosine 45 is going to be positive according to the sign convention, and TC cosine 30 is going to be positive as well according to the sign convention. And then the summation of those two forces should equal 0. So you have FA cosine 45 plus TC cosine 30 is going to equal 0. Here we have two unknowns and we have one equation. It cannot be solved. Then I'm going to use the second equation, which is the summation of the forces in y-axis should equal 0. Again, the sign convention is very important. Now we are going to look at all the forces in the y-axis. We have FA sine 45 is going to be positive according to the sign convention. We have 3 kilonewtons is going to be negative according to the sign convention. We have FB is going to be positive. We have TC sine 30 is going to be positive as well. So we are going to have FA sine 45 positive. We have 3 negative. We have FA positive. We have TC sine 30 positive. The summation should equal 0. Here we have FA unknown. We have FB unknown as well. We have TC unknown as well. We have 3 unknowns. We have 2 equations. It cannot be solved. So I'm going to use the third equation. Like I said that you have to be smart about the third equation. You need to use allocation where you have only one unknown. So if you are going to choose point A, if you are going to take the moment about point A here, you are going to have FB, which is unknown. You are going to have TC, which is unknown as well. So it doesn't work here. So it's better, for example, if you may say that I'm going to use the point B. If you are going to take the moment about the point B, you are going to get FA, you are going to get FC. Also, again, you are going to end up with 2 unknowns. I'm thinking about how to get only one unknown. So if I'm going to choose the point C here, you are going to end up with only one unknown, which is FA, because TC here and here, the line of action is going to pass through the point of rotation. The same goes for FB, which means that those unknowns are not going to be included in your equation. So that is why I'm going to take the moment about the point C. Again, the sign convention is very important. Any force that we are going to cause a moment clockwise is going to be a negative. Any force is going to cause a moment which is counterclockwise is going to be positive. Then now here at the point of rotation, I'm going to start with FA sine 45. I'm going to draw the line of action. Then I'm going to draw the shortest distance from the point of rotation to the line of action. You are going to figure out that the distance is 4. So I'm going to multiply 5. I'm going to multiply FA sine 45 times 4. And if you fix that point, you push from here, you are going to figure out that the rotation is clockwise, which is minus. So here I have minus FA sine 45 times 4. Then I have FA cosine 45. Again, here is the point of rotation. I'm going to draw the line of action here. Then I'm going to draw the shortest distance from the point of rotation to the line of action, come out to be 1.5. So I'm going to multiply FA cosine 45 times 1.5. Of course, if you put sine 45 or cosine 45, it doesn't really matter because sine 45 and cosine 45 are the same. Then I'm going to move to 3 kilonewton here, draw the line of action, draw the shortest point from the point of rotation to the line of action. You are going to figure out the perpendicular distance is 2 meters. So I'm going to multiply 3 kilonewtons times 2 meters. And if this is a point of rotation, you push from here. The direction is going to be counterclockwise. Then you are going to is going to be clockwise, and then the moment is going to be positive. So we are going to have positive 3 kilonewtons times 2 meters. Finally, here we have a couple moment. Again, please take care. Do not multiply the couple moment by the any distance here. It's already a moment, so please do not multiply by any perpendicular distance. I've seen this a lot. Many students multiply the couple moment by a distance. So it doesn't work this way. It's already a moment. And also some students, they are going to include the couple moment inside that equation and that equation. This is a moment. It cannot be included here or here. So please take care of that, since the direction is clockwise, so it's going to be negative. And the summation of all of this moment should be 0, because the system is in equilibrium. Now I have only one unknown, which is FA. I have one equation, one unknown. Easily I can get the FA. So FA came out to be minus 1.313 kilonewton. That means that the real direction is opposite to the one which is assumed here. And then once I have FA, I can get back to equation number 1, which is here. I'm going to substitute the value like that. Don't forget the minus. Then you are going to get the value of TC. So TC came out to be 0.924. Then substitute TC here and substitute FA here, and you are going to get the value of FB. So here is the good example. It's contain a lot of challenges. Make sure that you have the ability to solve that example. Of course, here you can imagine many situations. For example, you could put a triangular distributed load here instead of that concentrated force. You could put a rectangular distributed load here. Imagine the situation and try to find answer for that. So anyone can easily put a problem regarding the equilibrium of a rigid body. But just make sure that you have a reaction which going to form a balance for the structure. The structure should be in equilibrium. So I'm going to stop here. If you have any questions regarding